Hi, I'm Marvin, and today I'm presenting our work X3KD, Knowledge Distillation Across Modalities, Tasks and Stages for Multi-Camera 3D Object Detection. As indicated by the title, in our work we address the task of multi-camera 3D OD, meaning that images from multiple cameras are processed by a neural network which outputs surround view 3D bounding boxes. As motivation to our work, we noted that LiDAR-based 3D OD models outperform camera-based 3D OD models, and we also noted that if we pre-train the backbone on instance segmentation, this clearly improves performance. This motivates our work where we extend the previous 3D OD approach by two contributions. We propose cross-modal distillation from strong LiDAR-based 3D OD teacher and cross-task distillation from a 2D instance segmentation model. Let's have a closer look at camera-based 3D object detection. So first, the images from multiple cameras are processed by a feature extractor and subsequently transformed to bird's eye view space by a depth-based transformation. The bird's eye view features are further processed by a B-event encoder and decoder, and finally the prediction head outputs the 3D bounding boxes, which are supervised by the losses from center point. So in our baseline BAV depth, which was published recently, a LiDAR is already used as supervision, but only to supervise the depth map used to transform the features to bird's eye view. So we did a small analysis on this approach and tested two things. So first we checked out what the larger view transformation has as an effect and what the depth supervision has as an effect. And we noted that the depth supervision has a rather small effect, but the bigger network architecture has the bigger contribution here. So the aim of our work is to find other ways of using the LiDAR model as supervision and to improve the model without inducing additional complexity during inference. So let's have a look on how we achieve that. If we compare camera-based 3D OD models and LiDAR-based 3D OD models, then we note that the feature extraction, the view transformation, BV processing, and prediction is more or less the same. So there are a lot of similarities in both models. If we have a look at the extracted BEV features, however, we note quite some differences. In the camera-based 3D OD model, we see very strong activations at the center around the car, which is basically because most of the pixels in the camera image correspond to locations which are kind of near to the car. On the other hand, if we have a look at the features extracted from the LiDAR, then we see that spatially we obtain much more balanced feature activations, which correspond quite precisely to objects in the scene. So essentially, we would like to encourage the camera feature activations to be similar to the LiDAR feature activations, and to improve the camera-based feature representation in bird's eye view. So how do we achieve that? We propose three contributions. First, we propose cross-modal feature stage knowledge distillation to encourage the camera-based features to be similar to the LiDAR-based features. We propose cross-modal feature stage adversarial training, which encourages modality invariant features, again enhancing the bird's eye view feature representation of the multi-camera model. And we propose cross-modal output stage knowledge distillation to supervise the camera-based models by pseudo-labels from the LiDAR teacher, which would also enable training on vast amounts of unlabeled data. Let's have a look at our second contribution, the cross-task distillation. Here we make use of a pre-trained instance segmentation teacher, which generates pseudo-labels. And these pseudo-labels are used to supervise an additional head, which we add to the camera-based 3D OD model during training. During inference, the camera-based 3D OD model stays as is, so no additional complexity is added during inference. So let's have a look at some results. So we evaluated our X3KD model in the state-of-the-art comparison on the new new scenes dataset, we can see here that our baseline BEV depth, which we re-implemented, achieves similar results than reported in the paper. We see that our method significantly improves on this baseline, and we can also see that all other approaches are outperformed by X3KD. We show this also at different resolutions. So we first look at the highest resolution which is possible on new scenes with the ResNet 101 backbone, again showing quite strong improvements over the previous state of the art. And we also submitted some results to the non-public test set, and we can see that the improvement also generalizes to the test set. In our ablation studies, we show the effectiveness of our single contributions by adding them individually, and we can see that adding all contributions at once achieves the best results in the main mean average precision and new scenes detection score metrics. We also provide some ablations on different variants of our method components. For the cross-task distillation, for example, we experiment with different backbones, and we show the effect of using pre-training and knowledge distillation, where we observe that pre-training and knowledge distillation together achieves best results. We also show that the output distillation removes the need for annotations, so we can apply our method also without using any ground truth at all and just using pseudo labels from the LiDAR-based teacher model. We can see that we have a bit of decreased performance, but it still works reasonably well. Also qualitatively, we can observe some improvements if we compare our output from our X3KD method to our baseline BEV depth. We observe improved detection and classification performance in terms of 3D bounding boxes. So let's summarize what we have done in our work. First, we introduced a cross-modal knowledge distillation from a LiDAR-based 3D object detection model to a multi-camera 3D object detection model. We also proposed cross-task knowledge distillation from a pre-trained instance segmentation model to the feature extraction of a multi-camera 3D object detection model. We provide the detailed ablation studies on the effectiveness of our single contributions, thereby showing their effectiveness. And finally, we outperform previous state-of-the-art approaches in various settings on the new scenes dataset, and we do not add any additional complexity during inference. Thank you very much for your attention.